In this video, we're going to be looking at a type of machine that was developed by a scientist named George Atwood back in the 1700s. This type of machine is still used to teach physics because it gives us an excellent look at how the parts of systems interact with each other and how dynamics affects objects that are attached to one another in a system. And that's what we're going to be looking into here. Now, this is a basic Atwood machine. This is the foundational Atwood machine that George Atwood was working with as he was doing his experiments. Basically, it was just a pulley with a string passed over the top and then two masses tied to the strings. Now, we would say that the pulley has to be as idealized as possible. An ideal pulley has no mass and no friction. Now, is it possible to get a pulley with absolutely no mass? Well, no, not in the real world. So in the real world, we would make sure that our pulley had negligible friction and negligible mass. The mass of the pulley itself is small compared to the mass of the system, and the friction is small compared to the other forces that are acting in the system. So small that we don't have to take them into account in the math that we're doing. And then it's also helpful for us to understand the forces that are acting on these objects. Now you can see in this picture, mass 1 is obviously larger than mass 2. In an Atwood machine, if we were to hang masses of the same size on either side of the pulley, the forces on those masses would be the same, and either the masses would be at rest and not moving at all, or they would move at a constant speed because of the balanced forces. Now again, in the real world, that friction in the pulley that's not perfectly frictionless would eventually cause the masses to come to rest. However, most of the time when we analyze Atwood machines, we have one mass on one side that's larger than the mass on the other side. What does that cause? Well, the larger mass is going to have a greater weight force than the smaller mass. And if we have a greater weight force on one side than the other, we're going to have an acceleration toward the greater force. Now, the interesting thing is that acceleration has to be uniform through the system because that mass is pulling a string that can't just stretch out. So the acceleration of mass 2 is going to be the same magnitude as the acceleration of mass 1. And then one other important consideration in an Atwood machine, the string does experience a tension force. And that tension force is applied upward to the mass on the right side of the pulley and upward on the mass on the left side of the pulley. So the tension has to be the same throughout the string. However, it will be applied in opposite directions depending on which side of the pulley we are on. And it's just important to keep those things in mind. It will become obvious how we're going to use these as we start setting up free body diagrams. Now, there are other types of Atwood machines in addition to the standard version. We have this version of an Atwood machine where we have a mass resting on a flat surface and then a pulley hanging over the edge of the surface, another mass pulling down. Or we can even incorporate an inclined plane into our Atwood machine. And I should just mention that the variations on an Atwood machine could be endless. What if we added a fan cart in, where there was actually a cart on one side with a fan adding an additional force, and then a pulley and a mass pulling down on the other side? That would still be an Atwood machine as well. So we can make different variations of this. These are some common variations that we will see in the original Atwood machine. And what makes these Atwood machines? Well, we have two masses connected by a string slung over a pulley. Those are important characteristics. A pulley and two different masses that we're analyzing. It could actually be more than two masses as well, but there has to be at least two different masses involved. When one mass accelerates due to gravity, the other accelerates in a different direction. And the other one might be affected by gravity, as it is in the traditional Atwood machine. Maybe the other one's affected by friction, as it is in the two non-traditional machines I have pictured here. Maybe it's affected by part of gravity pointing down the slope, like in our inclined plane Atwood machine that I've pictured here. So again, there's a lot of variations, and I'm going to show you how to think through an Atwood machine problem regardless of the way that it's set up. And we're going to start actually by working a traditional Atwood machine problem first. We have a 200 gram and a 50 gram mass connected by a length of string. The string is run over an ideal pulley. If the masses are arranged so they have room to fall or rise when released, find first the tension in the string and second the acceleration of the system. Now, personally, I think it's easier to find acceleration, so I'm going to go ahead and find acceleration first, and then I'm going to find tension. However, you could do this either way. There's a lot of variations in how you solve these. You just have to know how the general setup of these works. And the general setup of an Atwood machine is the same as the general setup of any dynamics problem. We're going to note the dynamics values that we know, the dynamics values that we don't know, but the key is we're going to analyze one mass at a time. We're going to set up a free body diagram for each independent mass. And then there's one pitfall that a lot of times people fall into when setting up Atwood machine problems. I'm going to point that out as well. Here's a diagram of our Atwood machine. This is just a traditional Atwood machine. We have a 200 gram mass on the right. We're going to label that M1, and a 50 gram mass on the left. We're going to label that one M2. The result is we're going to have acceleration toward the more massive mass, the one on the right. And we have the same acceleration, but in the upward direction on the left-hand side of our Atwood machine. Let's go ahead and note some of the things that we know and don't know in our dynamics table here. Do we know the mass of M1? Why, yes, we do. It's 200 grams, or I'm going to just convert it right away because I know we're going to have to convert it to kilograms. Anytime we're working with newtons in a problem, we need to make sure that we're using kilograms and not grams, because a newton is a kilogram meter per second squared. So we do have to make sure that we convert. 200 grams is 0.2 kilograms, so I'm just going to include that value. We also know the mass of M2, 0.0500 kilograms. Do we know the acceleration? Actually, the acceleration is one of the things that we're looking for. So I'm just going to note that with a question mark for now. I am going to need to find the acceleration. Now, before I go down and list any of the forces that I know, maybe it's a better idea to start by drawing some free body diagrams of those forces. And here's the thing. In an Atwood machine, you may be tempted to try to combine the forces acting on both masses into one free body diagram, but it doesn't work that way. Free body diagrams are only able to analyze one object at a time. So we're going to need separate free body diagrams for M1 and M2. And we're going to see that some of the values in these free body diagrams seem like they would be obvious, but they're not necessarily. All right, so let's take a look. The free body diagram for M1 is going to look like this. I have a weight force pointing downward, Fg1, and a tension force pointing upward. The rope is actually what's making contact with the mass, pulling it upward. Now, you may be tempted, here's the pitfall I was talking about. You may be tempted to call the tension the weight force of the smaller mass, because isn't that what's opposing the motion of this larger mass downward? Well, because there's also acceleration happening, you don't know for sure that the tension in the string is just the other mass's weight. And in fact, I can tell you that in all cases where we have two different masses on either side and an acceleration, the tension is going to be different. It's not just the weight of the other object. It's also going to be influenced by the acceleration of the objects downward on one side of the pulley. So we don't know what the tension force is. And just a reminder, you're going to be tempted to say that the weight of the other mass is the tension force, but that is not correct. All right, so now let's set up a vector addition problem for these vectors that we have. And this is what it looks like for my larger mass, M1. I'm going to have my tension force pulling upward. I'm going to add to that the gravity force pointing downward. I notice that there's a downward net force for my larger mass. And that makes sense, coherent sense, because there's a downward acceleration for the larger mass. So I would expect to see a downward net force in my vector addition problem. Now, separately, let's make a separate free body diagram for the second mass. The second mass is affected by the same forces, but they're going to have different magnitudes. So the second mass is affected by a tension force pulling upward. Now, that force in particular has the same magnitude as the tension force on the other side. The tension has to be the same everywhere throughout the string. So this T is equal to the T from the other side. However, the gravity force is different, and we're going to see in a moment the net force is different. When I add these vectors together, I'm going to find that there's a net force on the other side pointing upward. But again, that makes sense because there would have to be an upward acceleration on the other side of the pulley for this system to make sense. And here's what I know about this. I know that the accelerations on either side have to be the same, and the tensions on either side have to be the same. Even though they're pointing in different directions, the magnitudes of those tension forces are the same. Okay, now that I have my free body diagrams drawn out, and I've made sense of what these different weight forces or gravitation forces are in this problem, let's go ahead and fill out the rest of my dynamics table. First of all, is there a constant that applies to weight force? Well, there sure is. It's G equals 9.8 newtons per kilogram. And when I multiply that times the mass of M1, I get FG1. So 200 grams is 0.2 kilograms times 9.8 gives me a force of 1.960 newtons. And then my 50 gram mass, or 0.05 kilograms times 9.8, gives me a weight of 0.490 newtons. All right, then what about the tension? Well, once again, I can't calculate tension from anything. There's no constants that help me calculate the tension force. Tension can only be found indirectly by figuring out all the other forces in my free body diagram and seeing how much tension there is to make everything either balance or to work out with the acceleration that I have. And again, I don't know what my tension is in this problem, so I'm just going to record that as a question mark. That's one of the questions that I need to answer. So here I have two unknown dynamics values that I need to solve for. I also have two separate free body diagrams. What if I can turn these free body diagrams into equations? Well, I can use my good old net force equations, or again, the sum of the external forces, the same thing as a net force. I can use those equations to get some relationships between the variables that I know. So let's go ahead and do that. First of all, for the first free body diagram, the sum of the external forces is Fg1, and I'm just going to make sure that I'm noting the direction right away with my signs. T is going to be pointing in the opposite direction of Fg1, and I'm going to define that downward on the right and upward on the left are going to be my positive direction. So maybe the best way to say it is the forward direction of motion is the positive direction. Notice that because I have a pulley, and remember the thing that pulleys do, they change the directions of things. Because I have a pulley in between, my positive direction is going to be different on the left side and the right side of the pulley. But I can say that the forward direction of motion here is always going to be my positive direction. And then any force that points in the opposite direction of motion is going to be negative. That's why tension here is going to be a negative force. All right, I also need to say whether this is going to be 0 or ma. Well, in this case, I do have an acceleration, so the sum of the external forces is ma. Set those equal to each other, and I have my first equation that has the tension and the acceleration in it. But I have two unknown values that I absolutely do not know. I have no idea what the acceleration is or the tension. So let's see if we can get some more information from my second free body diagram. My second free body diagram, remember, is for M2. So we're going to be looking at the second mass here as we come up with our equations. What forces are acting on M2? Well, in this case, I have a negative weight force because now gravity is pointing in the opposite direction of motion, and a positive tension because tension is pointing in the direction of motion. Notice that tension is acting in opposite directions on either side of the rope. That's just one of the things that tension does. When we have two objects connected to each other by a rope, tension is going to pull one way on one object and the other way on the other object because tension always pulls in the direction of the attached rope or string or wire. And that's why tension is positive in this case, but it was negative in the other case. It's actually pulling in the opposite direction on this object. All right, now, we also need to include a statement about mass and acceleration. Well, we know that there has to be acceleration, and not only does there have to be acceleration, there has to be the same acceleration for the second mass as the first mass. Because both of these are attached by a string, they have to be accelerating the same amount. So A here is the same as it was previously. And then I'm just going to combine these equations together, just like we always do with net force equations, into a single expression. But I'm going to take this one step further, and I'm going to solve this to get T on a side by itself. So to get T on a side by itself, I just have to add Fg2, so the weight force on object 2, to both sides of this bottom equation. And then I have T on a side by itself. Now, why did I do that? Well, do you notice what I have here? I have a system of two equations with two unknowns. And those unknowns are the same in the two equations. So what I could do is I could use any technique I want to where I have two equations with two unknowns to solve for the unknown values. And if I wanted to, I could go ahead and start plugging some of the values in. I know a lot of the values that are in here. The only values I don't know are T and A. So if I wanted to plug in those values and then solve for, the solution to the system of equations, I could do it that way. I'm actually going to leave my equation in symbolic form for now until the very end. I'm not going to plug in any values yet. And I'm going to use substitution to solve. And in doing so, I'm going to take you through deriving a very common equation for Atwood machine acceleration. Let's go ahead and do that. So here I'm going to combine the Fg1 minus T equals M1A equation, and I'm going to substitute in for T the bottom equation, T equals Fg2 plus M2A. And I get this equation when I combine those two. Now just look at what this equation is saying. The weight force of my larger object minus the weight of the smaller object, because that object is pulling backwards on it, minus the second mass times acceleration equals the first mass times acceleration. Now that first part of the equation is a little easy to understand. The second part's not so easy to understand, but maybe it'll become a little more clear what's happening here as we go through and derive this a little bit. I think my next step is going to be to get acceleration on a side by itself, because I need to solve for acceleration anyway. So what I'm going to do is I'm going to get any term that has acceleration in it on one side of the equation, and that's going to look like this. Notice I also flipped the equation around to bring A over to the left side because we're going to be solving for A, and usually you put the thing that you're solving for on the left-hand side by convention. Please verify that the equation below is the same as the equation above. I just used valid algebra techniques to get here. All right, the next thing I'm going to do is factor out an A on the left side. So I find that A times M1 plus M2 equals the weight force of object 1 minus the weight force of object 2. And then I'm going to divide both sides by M1 plus M2. And I would say this is probably the most significant equation because this is the one that actually kind of helps you make sense of what's going on here. So if I take the total force pulling downward, the net force pulling downward, what is that net force pulling downward in my system? Well, that's going to be the weight force of object 1, which is pulling downward more strongly, but actually that's being resisted by the weight force of object 2, Fg2. So I'm going to subtract the weight force of object 2 from that, and that should give me the actual total force pulling these masses downward. But that's not going to tell me what the acceleration is directly, because force still includes the mass. So I'm going to have to divide out the mass. Which mass am I going to divide out of this? Well, I'm going to have to divide out the entire mass of the entire system, right? Because the entire system is being accelerated with the same acceleration. How do I get the entire mass? Well, I just add together M1 plus M2. And that's what this equation is saying. And you see, if I rearrange this, do you notice this kind of looks like F equals ma? It's just that there's two forces listed, two opposing forces listed, and then there's two masses for the two objects. So this equation kind of makes sense. Now, here's the key though. Don't try to memorize an equation that kind of makes sense. Make sure you know the process we use to get here, because that process always works. So what do we do to get here? We set up free body diagrams for each object individually, because that's what we can do with free body diagrams. So you can analyze one object at a time. And that's exactly what we did. We analyzed the more massive mass and then the less massive one, M1 and M2, separately with separate free body diagrams. We noted that tension was going to be the same throughout the string because that's just how strings work over ideal pulleys. The tension's not going to change throughout the string. We also noted that the acceleration has to be the same, just logically. So we combined our net force equations, and then we combined two equations with two unknowns to solve for one unknown, acceleration. Now, I know FG1 and FG2, but I just want to make this look a little fancier than it is right now. There's another version of this that you may see sometimes. So I'm just going to show you that. And what that does is it breaks these gravitational forces into their mass times gravity expressions. So we'd have M1G is equal to the force of gravity on object 1, and M2G is equal to the force of gravity on object 2. And the reason that this is done is you can factor out an extra G from this, and it just makes it look a little fancier than the previous version. But it's the exact same thing as before. Interestingly, from this equation, we can draw a conclusion as well. M1 minus M2 is always going to be less than M1 plus M2 because mass is always positive. So that last expression in parentheses there is always going to be a fraction. It's going to be less than 1. And we're going to be multiplying G, which is the acceleration due to gravity at the Earth's surface, by a value that's less than 1. Does it make sense that our acceleration is going to be less than the free fall acceleration? Because we have a mass on the other side of the pulley that is pulling backwards and opposing by a certain amount. So this equation also helps us make sense of what's going on, understanding an Atwood machine in terms of a proportion of the gravitational acceleration. Okay, so just different ways of understanding this. Again, it's not really important that you understand it that way. What's most important is that you're able to start from scratch and get to this final result if you have to. All right, let's just go ahead and plug in the values that we know. We're just going to use that final equation that we developed. I know we already calculated the forces, and it would probably be easier to use that force equation, but let's just use this final equation. Any of these will give us the same values anyway. So I know G is 9.8 meters per second squared. I could also use newtons per kilogram. It really doesn't matter what I use in this case. And then I'm going to multiply that by M1 minus M2, which is 0.2 kilograms minus 0.05 kilograms, over the sum of those two values. And when I work that out, I get an acceleration of 5.88 meters per second squared. And that's pretty much what I would expect. It's going to be less than acceleration due to gravity, but it's going to be biased toward being a faster acceleration because I have a 200-gram mass, which is a pretty big mass on one side, and the mass opposing it is fairly small, 50 grams. So 5.88 makes logical sense. I'm going to go ahead and record that in my dynamics table as the acceleration. Now, can we figure out what the tension was? Well, I have two equations I could use to figure out the tension, and if I have two equations to do it, I might as well just use them both and verify that I have the right value. So I'm going to go ahead and plug in acceleration into my first equation that has tension in it. This is the combined net force equation from my first free body diagram. And because I'm solving for tension, I'm going to get tension on a side by itself. And just notice that I'm starting with here negative T on the left. So I have to change the signs of everything after I move everything over. And I get that tension is equal to the gravitation force on object 1 minus mass times acceleration. And now that I know mass times acceleration, I can figure out what tension is. Also, just notice from this equation that the tension is affected by the acceleration. And that's why we couldn't just from the very beginning say that the tension must be the weight of the mass on the other side of the pulley, because it is affected by the acceleration. So if I go ahead and solve this for T, I'm just going to plug in what I know. I calculated my gravitation force on mass 1. It's in my table. I know the mass of that mass, and then I know my acceleration now. And I get a tension of negative 0.784 newtons. But hold on, I've got another equation I should be able to use to verify that. That's my tension equation that I calculated from the second free body diagram. And that one's already in terms of T at the very bottom. So let's just plug in what we know to that equation for T. Fg2 was 0.490 newtons, and the mass of mass 2 was 0.05 kilograms. I'm going to multiply that times acceleration, and I get the same tension, just the opposite direction. And when I report tension, I'm just going to go ahead and report the positive value, and then I will decide whether it's positive or negative depending on the application, if I have to use it in an equation again. And I'm going to go ahead and record that in my dynamics table. 0.784 is the tension in the string. Now that we finished working a problem with a traditional Atwood machine, let's move on to a problem with a modified Atwood machine. And let's see what that modification is. So here we have a 0.20 kilogram block placed on a 30-degree incline plane. Block is connected to a mass M2 by a string that passes over a pulley to the top of the incline. Oh, mass M2 is also 0.2 kilograms and hangs vertically from the string. Wait a second, if we have two masses that have the same mass, shouldn't they hang without acceleration on an Atwood machine? I wonder how this is going to play out. Oh, wait, but it's on an incline plane. So that makes this a modified Atwood machine because we're not dealing with mass versus mass in the sense that the weight is pulling down on each one. One of them, the weight is pulling fully downward. The other one, only a component of the weight is pulling downward. So this one still should be accelerating. The coefficients of friction for the block and the plane are 0.4 for static friction and 0.3 for kinetic friction. But if we're only looking for one acceleration, one value, we're going to have to choose one of these two coefficients. We can't use both of them in the same problem. So what's it going to be? Well, let's read the next sentence. If M2 is released from rest, that phrase from rest makes me start leaning toward static friction, but then M1 is able to slide up the ramp. Sliding up the ramp makes me lean toward kinetic friction because it's moving. What is the acceleration up the ramp? Well, let's just figure this out once and for all. Acceleration up the ramp, if it's accelerating up the ramp, that means that it's moving. It has to be moving to be accelerating. Therefore, we're going to use kinetic friction because it's moving, not static friction. And I can completely ignore the static friction value because it's just extra information that I don't need. All right, so maybe it would help for us to visualize this by making a diagram of it. What does this actually look like? Here's our modified Atwood machine. I have M2 and M1. I have M1 pictured as a little bit larger because sometimes it might be, but in this case, M2 and M1 have the exact same size. So even though M1 is larger, it has the same mass as M2. And what are some of the forces that are going to be acting here? Well, on M2, I have a gravitation force acting downward and a tension force acting upward. That tension is going to be the same throughout the wire or the string, by the way. Now, I know that M2 is going to be completely pulled down by gravity, but only part of M1 is going to be pulled down the incline by gravity. So this is going to be accelerating toward M2 probably. We'll work out the math, but we're going to expect that the acceleration is going to be this way, and that means that M1 will be accelerating up the ramp. What are my forces acting on M1? Well, I have gravity pointing straight downward, friction opposing the sliding motion up the ramp, and a normal force perpendicular to the ramp. There's also going to be another force of tension, right? Because that wire or string is pulling this block up the ramp, and the tension force has to be in the direction of the string. So one of these forces doesn't conform to the coordinate plane that's in the direction of motion, and that's my gravitation force. I'm going to need to take that gravitation force and break it into components. How am I going to do that? Well, first of all, I need to take into account the incline of the inclined plane is 30 degrees, and then I can set up a little force component triangle showing the components of the gravitation force I need to get all of my components in the correct tilted plane for this block that's moving up the inclined plane. So I'm going to have FG perpendicular, FG parallel, and I'm just going to go ahead and replace FG1 in my diagram with those components right away, because those are the components I'm actually going to be using to solve this problem. And there I have my diagram of all of the forces that are going to be acting. This helps me to understand this problem a little bit more. But now we still need to do a little bit more setup before we solve this problem. Let's go ahead and make our dynamics values table. And I'm going to make dynamics values entries here for two different masses, which means this is going to apply to two different free body diagrams I'm going to have to make. I know that M1 and M2 are 0.2 kilograms. I do not know the acceleration up the ramp, but I'm going to find that by calculating it from what I know about this problem. That's what I'm looking for. Let's see, do I know FG1? Well, that's the vertical force of gravity acting on my block that's on the slope. I have a constant that will help me solve for that, 9.8 newtons per kilogram. So I'm going to go ahead and multiply that times the mass of 0.2 kilograms to get a force of 1.96 newtons. That's the vertical version of that FG1. The actual FG1 value, I'm going to need to break that apart into its components though. I need to know how much of that 1.96 newtons is perpendicular to the ramp and how much is parallel to the ramp. And to do that, I'm going to have to use some constants associated with trigonometry, the cosine of 30 and the sine of 30. Now, sine of 30 I just know is equal to 1/2 from the AP equation sheet, and just what I know about trigonometry as well. Cosine of 30 is another special value, but it's you just have to punch that one into a calculator. Okay, so let's go ahead and calculate the perpendicular component. That's going to be the one that's FG1 times the cosine of 30, because in my diagram, my component diagram, that's the adjacent side. The perpendicular side is the adjacent side. So I'm just going to take 1.960 newtons times the cosine of 30, and that gives me 1.7 newtons pointing perpendicular to the ramp. Sine slides. So this sine function is going to be used multiplied by FG1 to give me the value of force pointing down the ramp. And if I go ahead and calculate that, I have 1.960 times the sine of 30, that's times 1/2, is going to be 0.98 newtons. I'm just going to go ahead and plug those values into my table. Now, when I plug in 1.70, I notice that that perpendicular value is going down from my coordinate plane, so I'm going to make that negative. And this G parallel value, for right now, I'm going to leave that without a sign. I might make that negative later, depending. Okay, so these positives and negatives I enter into the table, keep in mind, you're going to have to think them through later on. I don't know whether I want this to be positive or negative at the moment. I'm leaning toward negative, actually, because if acceleration is in a positive direction, this is going to be pointing opposite the direction of acceleration. But for right now, I'm just going to leave this positive and make the actual decision later. You always think through your signs when you actually plug in the values into your equations. But what about friction? Well, I know the coefficient of friction is 0.3. That's the one that we chose because it's kinetic. But I don't know any of the other forces I need to know to find friction yet, right? Well, let's go ahead and figure some of those out. And the way we're going to do that, let's start setting up our net force equations. Our first net force equation is going to be that the net force is equal to all of the forces acting on M1. So we're zeroing in on M1 for right now, that mass. We're not going to do M2 right now. And what are all the forces acting on mass 1? Well, it's Fg parallel plus the force of friction plus tension plus the normal force plus the perpendicular force. And I grouped these forces so that the two quote-unquote vertical forces, the perpendicular forces, are at the end. I'm also going to note that when I do add these forces up, I have an acceleration. So F net equals ma. And I can go ahead and cross off these two forces at the end because they are not in the same direction as my acceleration. They're perpendicular to my acceleration, and they cancel each other out. Now, whenever I cancel out forces, I can note that those two forces added together equals 0, or one of those forces, if there's two of them canceling out, one of those forces must be equal to the opposite of the other. And normal force is actually a force I can use to figure out what friction is, mu times the normal force. So I'm just going to go with this. I know what the value of Fg perpendicular is. It's negative 1.7 newtons. So if I plug that in, I find that the normal force is positive 1.7 newtons. And then the force of friction, which is mu times the normal force, ends up being 0.3 times 1.7 newtons, or the force of friction is 0.5 newtons. I can go ahead and include that in my table, and again, I'm not going to put a sign on that right away, but again, I'm strongly leaning toward that that's going to end up being negative because it looks like the friction force is pointing opposite the direction of acceleration. I think I'm going to make the direction of acceleration positive. Okay, there's only one other value in my table that I don't know yet, and that's FG2, but that one's easy to find because it's just mass times the constant G, 9.80 newtons per kilogram. So 0.2 times 9.8 is 0.1960 newtons, and that is a force that's actually acting here. I don't need to break that one down to components because it's acting in the direction of acceleration already. And then just to note, I can't figure out what the tension force is directly. There's no constants that I can use to calculate it. I'm going to have to figure it out indirectly from all the other values that I know. All right, before I started a good thing, I started putting together my net force equation. So let's finish that good thing that I started. I have the net force equations written out for M1. I can combine those because they both equal the net force, or the sum of the external forces. And I get M1 times acceleration equals negative Fg parallel. I'm going to make that negative because it's pointing to the left, and the acceleration is pointing in the other direction. Acceleration is going to be positive in this case. Negative the force of friction, and then positive tension. Okay? What about my other net force equation for my other free body diagram, the free body diagram that's on M2? Well, that one, let's see, I just have two forces acting on M2. There's going to be gravity pointing downward and then tension pointing upward. And my next step is to decide whether this is going to be MA or 0. And once again, if I have acceleration for one object, the other one has to be accelerating at the same rate. Both of these are accelerating, so these are equal to MA. Now I'm going to put these together, and I'm going to worry about the directions or the signs that go on each one. One of these is going to have to be positive because it's pointing in the same direction as the acceleration. One of them is going to be negative. And the way that this works out, we're going to make Fg2 positive because it's pointing in the same direction as acceleration. T is going to be negative. And again, that makes sense too. Notice that the tension is negative on one object but positive on the other object. And that's what we would expect to see. Okay. I'm going to solve this final equation to get T on a side by itself, and then I can do a substitution. So T equals Fg2 minus M2 times acceleration. And go ahead and verify that I did my algebra correctly there. Now I'm going to plug in Fg2 minus M2a for T in the equation up above, because I'm going to combine the two net force equations that I developed together, because it's a system of equations with two unknowns, and that's one method of solving. So when I combine the two equations together, I get this long expression. Let's just take a look at what this expression is saying. So I have a mass times acceleration values on both sides. And in fact, I'm going to end up combining those mass times acceleration of object 1 plus the mass times acceleration of object 2 to get acceleration on a side by itself. That's what I'm going to do in the next step anyway. But let's look at the other side of the equation. I have negative the force parallel to the plane, force of gravity pulling downward on object 1, minus the force of friction. Okay, so I'm adding a negative friction there, and then plus Fg2. So notice that I'm adding together my forces that are pulling backwards as negative forces, and then plus the force that's pulling forward. So I have basically another net force term here for the entire system. How much force is actually pushing forward, or I guess pulling forward, on this entire system. I'm going to do the same thing here. I'm going to take all those forces and combine them, and then I'm going to divide them by the combined mass, because look how this works out. Acceleration is going to factor out, and then to get acceleration on a side by itself, I need to divide both sides by the combined mass. And then up on top of this, you see that I have the negative forces combining with the positive forces, and that's going to give me a net positive force. And then I divide that by the mass of everything to get the acceleration. Okay? And if you don't understand the explanation that I just gave, just do the math, because the math will lead you to this exact place. Just do the algebra. Make sure you're doing the algebra correctly. You do need to think through what's a positive and what's negative. What's in the direction of acceleration, positive, and what's opposite the direction of acceleration, negative. But just make sure you keep your signs straight, do the math, and you'll end up at this point. And at this point, I can go ahead and plug in values because I know all of these values. I know Fg parallel. I know the force of friction. I know the force of gravity pulling downward on object 2. That's greater than, notice that that value is greater than the values of the parallel force and the friction force combined. So there's going to be a net pull to the right or forward, or I guess downward in this case. Then I'm going to divide that by the total mass to get the acceleration of the system. The acceleration is 1.2 meters per second squared. All right, and I'm going to go ahead and plug that into my dynamics table, but I notice there's one dynamics table value that's still missing that we can calculate. We weren't asked to find it, but let's go ahead and find it, and that is the tension in the string. To find the tension in the string, we're going to just plug acceleration back into one of our net force equations, one of our resulting net force equations. So when I combine net force equations for the first free body diagram, I got this equation. And I'm going to rearrange this to solve for tension. Plug in the values that I know, and I know all of these values. I know the mass of object 1, its acceleration. I know the parallel force pulling down the ramp, and the friction force. Now notice that when I rearranged this equation, when I originally wrote this equation, I accounted for Fg parallel and Ff being negative. But when I rearranged the equation to get T on a side by itself, all of these are being added together. That's because the tension has to overcome both of the negative forces, the force of friction and the force of gravity pulling down the ramp, and the extra bit of acceleration, that MA value. So that's what this equation is telling me. I find that my final tension is about 2 newtons. I had to round this to one significant figure because my coefficient of friction was one significant figure. Coefficient of friction is a really hard value to get very precise. You remember we measured coefficient of friction in class. We had these distributions of points that looked really sloppy, but we were able to fit a line of best fit to them anyway. But you don't have a really precise value, and that's our problem here. So this was probably more like 1.7, but I had to round it up to 2 to get to one significant figure. All right, what about if I use the other equation? The other equation I have for tension from my second free body diagram is this one, Fg2 minus M2A. This one's actually a lot simpler because there's only 2 values in it, 2 forces, the tension force and the gravity force on object 2. And then I also have to include mass times acceleration. Well, let's go ahead and plug in the values that we know. We know Fg2 is 1.96, and I'm going to subtract from that 0.2 kilograms times 1.2 meters per second squared. If I did everything right, this should calculate the same, and it does. Calculates out to about 1.7, which we have to round to 2. So 2 newtons is the correct value for the tension in the string in this problem. And that's how you solve an Atwood machine problem. So hopefully you noticed some trends in these Atwood machines problems. You should have noticed that when we solve these Atwood machine problems, we start with free body diagrams for both objects on the Atwood machine. If you have more than 2 objects, let's say sometimes you'll have 3 objects on an Atwood machine or 4 objects on an Atwood machine, you have to combine objects that are on the same side of the pulley into one object. So if I had a 2 kilogram mass connected to a 3 kilogram mass on one side of the pulley, and then a 10 kilogram mass by itself on the other side, I would treat that like a 5 kilogram mass on one side and 10 on the other. We didn't work a problem like that, but that's pretty straightforward. So you're going to draw a free body diagram for one side of the pulley, a free body diagram for the other side of the pulley. You're going to come up with equations that include acceleration and tension, but those are going to be unknowns in your 2 equations that you come up with. And then you're going to have to use some method of solving a system of equations with 2 equations and 2 unknowns to find what those unknown values are. And that's how you do Atwood machine problems and modified Atwood machine problems.